This is the first of two modules where we will introduce you to the modeling of defaultable bonds. In this first module, we will introduce a modified binomial lattice for pricing short rates with default. We will show you how to price zero coupon bonds that are default free and zero coupon bonds that have a default and have a recovery associated with them on this binomial lattice. A defaultable bond is characterized by a coupon payment C, the face value F, and the recovery value R, where R is defined as the random fraction of the face value recovered upon default. We also have to specify the probabilities of default. When would the default events happen? What is the rate at which they are going to happen? And so on. As before, we will work directly with the risk-neutral probability Q. We will model the term structure of default, that is the time dependence of default probabilities, using a one-step default probability H of t, which is defined as the conditional probability that the bond will default over the interval t to t plus 1, given the information at time t. So ft will represent the information at time t. This is the conditional probability that the bond is going to default over the next period. As in the case with other fixed income securities, we are going to calibrate H of t to market prices. And we will modify the binomial lattice to include defaults. Just as a review, let's look at the binomial lattice for short rates. The nodes in this lattice were labeled I and j. I went from 0 through n. J went from 0 through I. So at time 0 you had one node. At time 1 you had two nodes. At time 2 you had three nodes, and so on. So each of these nodes were being labeled I, j. There was a short rate at all of these nodes, R, I, j. And the transition probability was given by the binomial lattice probability. So at time I plus 1, you could only reach states j and j plus 1. The probability that you went from node ij to node I plus 1, j plus 1 was QU, the upper probability. So here's QU. The probability that you went from node ij to node I plus 1, j, it's going to be Q of D. And the probability of reaching any other state is going to be 0. This was the short rate lattice that we worked with when we were constructing the short rate lattice for default free bonds. Now, in order to model default, we are going to split the node ij by introducing a new variable that encodes whether or not default has occurred before date I. ij0 will denote the fact that the state is j on date I and the default time tau is greater than I, which means that at time I or date I, the default has not happened. ij1 will encode the fact that the system is in state j on date I and the default has already occurred at some point before I. And when I say before I mean it includes I as well. Now, for the split lattice, for these split nodes, I'm going to tell you what the transition probabilities are going to be. Again, these transition probabilities are going to be risk-neutral transition probabilities. So let's work through this figure slowly. Here's my state at date I. And here are the possible states at date I plus 1. So here is date I plus 1. When we looked at the short rate lattice, we had nodes ij. Now we have split each of those nodes into two nodes. ij0 means default has not occurred. ij1, which means default has occurred. So the red nodes here indicate the fact that these are the nodes associated with states where the default has not occurred, and the black nodes are referring to the fact that these are the states at which the default has occurred. So what are the transitions out of the state ij0? This is the state where the interest rates are in state j, the date is I, and the bond has not yet defaulted. Then, with probability QU, you can go to state j plus 1. At that point, there are two possibilities. Either you can default or you do not default. So up here, it's QU times 1 minus Hij is the probability that you go to state j plus 1 without default. QU times Hij is going to the probability that you go to state j plus 1 and now you have defaulted. So instead of going from a red node, now you've gone to a black node. What about the down probabilities? They are the same. It's going to be QD times 1 minus Hij. This is the probability that you start from state ij0 and go to state I plus 1 j0, meaning no default and no default at time I plus 1 as well. What about the probability that you default at time I? It's going to be QD times Hij. Okay, so this table emphasizes the same thing. Qi plus 1 S eta. Eta is the label for whether there is a default or not. S is the label for the state. You can only go, if you go to state j plus 1 and eta equals 1, which means default, the probability is QU Hij. If you go to state j plus 1, eta equals 0, which means no default, the probability is QU 1 minus Hij. This is exactly the same probabilities that I just wrote on the figure. What happens to the transition out of the default state? So the transition from the default state are actually very simple. Once the bond has defaulted, we are going to assume that there is exactly one default event between dates 0 through n. So once a bond has defaulted, it's always in the default state. So from this particular default state, you can go to state j plus 1 and default, and you can go to state j and default. You can never go to the non-default state. So notice that there are no blue arrows or black arrows going to the state with no default. What is the probability of going to the state j plus 1? It's the same as the short rate probabilities. So this is going to be QU and QD. The hazard rates, or HIJs, which are the conditional probabilities of default, are not going to play a role in this transition, because once the bond has defaulted, it never reappears and always stays in the default state. The conditional probability of default, Hij, is state dependent. It's labeled by both I and j, and therefore this is date I, and this is the state and that particular date. Okay, once we have specified the transition probabilities, we can now start thinking about how we are going to price simple securities using this binomial lattice, and also how we can use these simple securities to calibrate both the interest rate lattice as well as this conditional probability Hij. So the first thing that we're going to start with is default-free zero coupon bonds. The default-free zero coupon bonds with expiration capital T pays $1 in every state on the expiration date capital T. These are default-free, so no default is possible. Let Z super Tij eta denote the price of the bond maturing on date I in node Ij eta, when of a default-free zero coupon. Just by context, this is what I mean here. So it's the same story. Earlier we had one node, now we have two nodes. This is Ij1 and this is Ij0. I need to specify what is going to be the price of a zero coupon bond in both of these states. The first thing we recognize is the fact that the default events do not affect the default-free bonds. So whether the default event has happened or whether the default event has not happened, the price of a default-free zero coupon bond is going to remain the same. So the price of that bond in both of these states are going to be exactly the same. So ZTIJ1 is going to be the same as ZTIJ0. And we're going to drop the state corresponding to default, since it doesn't matter to a zero coupon bond, and just call it ZTIJ. When we do risk neutral pricing for this default-free zero coupon bond, it's the same as that was seen in the term structure modules. ZTIJ is simply 1 over 1 plus Rij. This is the short rate in node Ij. QU ZTI plus 1j plus 1, QD ZTI plus 1j. So this is the expectation of the prices one time step later according to the risk neutral probabilities, discounted back to time I. And as before, as you saw in the modules corresponding to term structures, we can calibrate the short rate lattice. That is, we can compute QD, QU, and Rij using the prices of this default-free zero coupon bonds and other default-free instruments. In the modules, we emphasize the fact that there are too many variables, and often one sets QU equals to QD equal to a half, and then calibrate the Rij to make sure that prices of all the default-free instruments work out to be correct. What about extending this idea to defaultable zero coupon bonds? So now the bonds that we are considering have the possibility that they are going to default. And when they default, we are going to start with the instrument that pays no recovery. So what does it mean? It means that these bonds pay $1 in every state at expiration, provided default has not occurred on any date t less than or equal to capital T. If a default occurs at some point, the bond pays 0. There is no recovery. Again, let's see what the pricing works out to be. Z bar Tij eta will denote the price of a defaultable zero coupon bond maturing on date T in node Ij eta. Since there is no recovery, we know that as soon as the bond gets into a default state, its price is going to be 0. The moment a default occurs, you don't get anything, and therefore the no arbitrage price must be 0. So ZTIJ1 is always going to be 0 for all default nodes IJ1. What happens to the price in the no default node? Now we can use risk neutral pricing. We know what happens to the transitions under the risk neutral probability. So the price at IJ0 is going to be 1 over 1 plus Rij. It's just a simple discounting. So there are 4 possible states that you can go to. You can go to state I plus 1, j plus 1 without default. You can go to state I plus 1, j plus 1 with default. You can go to state I plus 1, j without default. And you can go to state I plus 1, j with default. What are the corresponding probabilities? It's QU1 minus Hij, QD1 minus Hij, QUHij, and QDHij. We already know that if you go into a default state, the price of a zero coupon bond with no recovery is going to be 0. So this term drops away. This other term also goes away because it's also a default state. So essentially, the risk neutral pricing for a zero coupon bond with no recovery is take the prices one time step later and discount them using the risk neutral probability. But the risk neutral probability now has 2 components, one that corresponds to the interest rate dynamics and another that corresponds to the default dynamics. Once you have the prices for all defaultable zero coupon bonds with no recovery, you can calibrate Hij using those prices. Now we want to interpret the prices of the defaultable zero coupon bonds with no recovery and try to understand or give an interpretation for what Hij is. The risk neutral pricing, by ignoring the 2 default state, essentially happens to be Z bar Ij0 is 1 minus Hij divided by 1 plus Rij, QU ZT I plus 1 j plus 1 no default, QD ZT I plus 1 j no default. This fraction here can be approximated by e to the power minus Rij Hij. And the quantity in the bracket here is actually an expected value with respect to a different probability measure, which we're going to call the default-free risk-neutral probability measure. What do I mean by default-free? What I mean is that all the default rates have been pulled out. So the price of a defaultable zero coupon bond is set by discounting the expected value by Rij plus Hij. And that's just coming from the expected, this expectation involves both the rates. So Hij has the interpretation of a 1 period credit spread. It's state dependent, it's time dependent, and it's a credit spread because if the bond was not defaultable, then I would have discounted only by Rij. But because the bond is defaultable, I'm going to discount the price by an extra interest rate, which is Hij, which is exactly the interpretation of a credit spread. The conditional probability of default Hij is also called the hazard rate. It's the probability of default given no default has occurred up to time I. Now let's extend this to the notion of recovery. I'm going to assume that the random recovery R tilde is independent of the default and interest rate dynamics, and let R denote the expected value of R tilde. As before, let Z bar Tij eta denote the price of a defaultable bond maturing on date I in node Ij eta. But now I'm going to emphasize the fact that this is after recovery, after whatever recovery amount has been paid. It's the X dividend or the X coupon. Here it's the X recovery price. Again, once the recovery has been done, there are no cash flows available from these bonds. We already know that Z bar Ij1 is going to be equal to 0 for all the default nodes. What about the no default nodes? The price there, Z bar Tij0, is going to be the discounted value of the prices in the future nodes as before. But now, if a default occurs, you get an expected value R, which ends up playing a role, and therefore the new risk neutral pricing for what happens to zero coupon bonds which are defaultable but have a recovery is this extra term shows up. And we'll stop here, and in the next module we're going to talk about how to price general bonds and how to use these general bonds or coupon paying bonds to calibrate the hazard rate.